Hi, I'm Fergus. I'm going to be presenting our paper, Intriguing Properties of Adversarial ML Attacks in the Problem Space. This is a joint work with Fabio Pierazzi, Jacopo Cortolazzi, and Lorenzo Cavallaro. So to set the scene, let's imagine a dystopian future in which pandas are forbidden, guilty of being too cute. And here there are detection systems everywhere using machine learning to detect pandas and lock them up. Luckily for us, pandas are very good at math, so they find some of the most important deep learning papers on adversarial attacks against neural networks, and they figure out which kind of adversarial noise they might add in order to evade detection. So here's a typical example where you have a panda classified with a certain confidence, and then you add some adversarial noise and it gets misclassified as a gibbon with high confidence. Let's say the panda wants to find a mask, a real-world disguise, using this technique to evade detection. So our panda goes down to the costume store, but unfortunately the optimal disguise that he's looking for isn't available, so he settles for a fox mask as the next best thing. He gives it a go and tries to sneak through as a non-panda citizen, but there are still many panda artifacts. He has chunky panda arms, panda legs, and a big panda belly, so he ends up getting caught. So let's talk about what happened a little bit more formally. Let's first consider traditional feature space attacks. In these attacks, you have an original image with feature vector x, you apply perturbation delta to that image, and obtain an adversarial image with feature vector x plus delta. To find this perturbation, you usually solve an optimization function by minimizing the sum of the pixel perturbation to keep the image realistic, and the loss of the target class so that the image is misclassified as that class. Let's consider a problem space attack in which the feature space and the problem space are very different. So here in the problem space we have some malicious application, and in the feature space we have a corresponding feature vector embedding. Following the feature space attack, we add some perturbation, for example by adding some API calls or strings, in order to obtain some adversarial variant that gets classified as benign. In this setting, you don't necessarily care how many features you modify. Instead, you have many other constraints. Is the new application realistic? Does it still work? Can the changes be truly detected? Is it still malicious? And then looking to other domains, are there some general constraints that we can consider? On top of that, we also have this problem of how to generate a functioning adversarial app based on our feature space calculations. This is the inverse feature mapping problem. And this is kind of the elephant in the room. In the image domain, the feature mapping is differentiable. You can backpropagate and discretize to find the new input. Whereas in the software domain, the feature mapping is neither invertible nor differentiable, so it's not immediately clear how to get back to a problem space example from the mutated feature vector, and perhaps the transformations you want to make just aren't available, like what happened with our panda friend. Nevertheless, there have been a lot of papers on problem space attacks across different settings, but it hasn't really been clear if the problem is solved, which attack is the best, and how to compare their strengths and limitations. There are two main contributions in this work. The first is a novel formalization of problem space attacks, which allow us to design and reason about problem space attacks in a principled way. With this, we can highlight relationships between the feature and problem space and derive some actionable points. Additionally, we propose a novel end-to-end adversarial malware generation approach for Android, which improves on limitations in prior work identified with our formalization. We also demonstrate that it's feasible to evade feature space defenses in the problem space at scale. And just to clarify, we focus on test time evasion attacks in this work, and we'll use code as a running example, but we'll also show how this applies to multiple domains. So let's move on to the formalization and start by covering some general problem space constraints that we've identified. First of all, we need to define which real-world transformations we can perform to automatically alter the problem space objects, and these transformations will correspond to perturbations in the feature space. So back to our code setting, we can perform some addition, like adding API calls, strings, or bytes, and similarly, we can remove those things, although this might have an impact on the functionality of the code, so we need other constraints to take care of that. We can also perform modification by combining addition and removal. Then we need to define which semantics do we need to preserve. Let's say we have part of a control flow graph here, and the malicious behavior occurs at the red node, and we want to ensure that that red node is still reachable in the adversarial malware. So in this case, removal might not be possible, but the addition of these yellow edges and yellow node would be a valid transformation because the red node is still reachable. In practice, semantic equivalence is undecidable, so we need to define a test suite to check that some set of behavior is preserved. Does it crash? Does it still phone home? Read and write the correct files? And so on. Alternatively, you might be able to preserve semantics by construction, by adding operations that have no actual effect, such as no-op instructions, or by otherwise ensuring any added code isn't executed at runtime. Next, we have to define what would it mean to be considered plausible. This captures the qualitative properties that must be preserved when mutating the object to ensure that it's realistic upon manual inspection. For this, we also define a test suite which might include user studies, but we can also approximate this manual scrutiny with some automated heuristics. For example, checking whether the app can even be installed or run at all. And now something that's often overlooked, which we call robustness to pre-processing. There have been many attacks, for example also the silence attack, where you start with some malware and you append some bytes to the end, and then the malware is immediately misclassified as goodware. But in practice, there are many program analysis approaches for removing unreachable code that could be applied and would strip out the features you need, completely defeating the attack. So in order to really compare the strengths of attacks, it's necessary to define which preprocessing methods your approach is robust against. So these were the four major types of problem space constraints we identify, and now we can reason a little more about the implications of this. So here's a toy example with two features, with the small arrow showing the direction of the gradient moving from the red area containing the points that are considered malicious to the blue area containing the points that are considered benign. Let's say we define a feature space constraint that we can only add features because we're worried about removing something important. So that would induce a feature space feasibility region, and only in this region could we find valid adversarial objects. Then there are the smaller problem space feasibility regions determined by the problem space constraints. For example, we might want to preserve the malicious semantics and be robust to preprocessing. Now say we start off with a malicious object X in the red area and we perform a feature space attack. As it's a feature space attack, we move within the larger feature space feasibility region following the gradient until we find delta star, which is the optimal feature space perturbation. So this is a valid feature space object, but it falls outside the problem space feasibility region, which means there's no corresponding object in the real world that we can generate from it. What we need to do at this point is to do a projection into the feasibility region formed by the problem space constraints. This causes what we call side effect features, which are features that don't necessarily contribute to the attack, but need to be there to ensure the existence of the problem space object. So some points here. Firstly, before considering a problem space attack, it might be useful to verify that a feature space attack is possible, because although the existence of a feature space attack doesn't guarantee a problem space attack, there can't be a problem space attack without one. Additionally, the maximum confidence of problem space attacks will be less than or equal the maximum confidence of feature space attacks. And if such an attack exists, and we can also find an approximate inverse feature mapping, then we'll be able to perform a problem space attack, although that mapping we find might end up being suboptimal. So just to summarize here, you see the reformulation of attacks in the problem space is somewhat more complex than the traditional definition of feature space attacks given the additional constraints. In the problem space, there are also different possibilities for search strategies. For example, a gradient-driven strategy where you use the feature space attack as a guide towards the optimal perturbation, problem-driven strategies where you blindly make transformations to the problem space object until it's misclassified, and hybrid strategies that combine the two. So this reformulation allows us to compare the trade-offs between different approaches and see where we might be able to improve on the state of the art. We have a very big table in the paper that shows how our reformulation, being a kind of extension of the traditional feature space attack formalization, can successfully describe domains such as image classification, facial recognition, and speech recognition, settings where the inverse feature mapping is not such a big deal, as well as characterizing the issues that come up in other domains such as malicious software and code attribution. And that leads us to the details of our novel white box attack for generating adversarial Android malware. So prior work has been vital in initially exploring possible attacks in the problem space, but by mapping them out with our reformulation, we can systematically spot areas that can be improved upon, in particular in terms of robustness to preprocessing and preserved semantics. So we start with some malicious software here that gets correctly classified as malicious, and so they ask for help from our doctor friend. With their help, we can use automated software transplantation to transplant code gadgets or organs from benign software to fool the classifier into thinking our app is benign. And we can use opaque predicates to ensure this new code doesn't execute and disturb the malicious semantics. And by using forward and backward slicing to only transplant complete realistic code gadgets, we can be robust to static analyses that detect and remove redundant code, and which should also help maintain the plausibility of the new app. So to give some more detail about the analysis we use to extract and harvest the organs, first we find the feature we need, say the presence of an activity in a benign donor. Then we choose a backward slice, a vein, which contains all the necessary logic leading up to the entry point. For example, creating the intent and starting the activity. Following that, we slice forward, say to get the activity definition, and then recursively follow any dependencies, for example, collecting any used permissions that need to be added to the manifest. Once we have the complete slice, we add it to an icebox, a database of organs ready for the attack. Then for the attack itself, given a trained target model, we first pick the feature with the greatest benign weight, find a corresponding organ from the icebox, wrap the organ in an opaque predicate to prevent execution at runtime, and repackage the new app with the injected code. Then we can repeat this over and over until the app is misclassified. Now relating back to the problem space projection, each organ, being a realistic slice of code, actually contains a number of side effect features. So it's actually more efficient for us to compute the total contribution of each organ by summing the target features, benign and malicious side effects beforehand, and then choosing the organs in order of their overall benign weight. And we can do that until the app is misclassified as benign. So now to turn to the main experiment in the paper. We use a dataset of around 170,000 apps with 10% malware, using a random split to remove the effect of concept drift as a variable. Then we choose two target classifiers. We choose Drebin, a linear SVM with a binary feature space, which is shown to still have state-of-the-art performance, and which also has a secure variant, SecSVM, which clamps the feature weights in order to force an attacker to make more and more perturbations than they would otherwise, because the feature weights are more evenly distributed. And then we use two confidence levels, one where we just cross the decision boundary, and a high confidence setting in which the new app lands much deeper within the benign region. So this plot shows the total number of features that we need to add in order to evade each classifier. And while the high confidence attack against SecSVM does require, in some cases, over 100 features to be added, this is still a small proportion of the total features. And in every case, we're still able to make those perturbations and achieve a misclassification without violating our problem space constraints. So it's informative to compare the statistics of the generated apps to the benign distribution to see whether adding all these features has caused our adversarial apps to become particularly anomalous or conspicuous. Here, the dark gray band shows the interquartile range for benign app size, and the light gray band shows the mean plus or minus 3 standard deviations, and we can see that the generated apps completely fall within these bounds. We can show similar results across a range of statistics such as the average cyclomatic complexity or the number of permissions or API calls, which gives us some peace of mind that our new apps will be sufficiently stealthy. In terms of time taken, in most cases it takes less than 2 minutes to create an adversarial example, and in total we're able to generate around 15,000 adversarial apps which show that these kinds of problem space attacks are a realistic and scalable threat. So with that, we can conclude. In this work, we proposed a novel reformulation of adversarial attacks, extending it to include the added complexity of problem space attacks, and used it to identify ways to improve on past work and develop a new attack in the Android malware domain. We also have a project website with some info, including the code, which we released on the 1st of May. And we believe that still, problem space attack research is just beginning, and there's exciting stuff ahead. So wherever anyone is, thanks very much for listening. See you soon.